afternoon session now, and our first speaker is Albrecht Giese, who's going to talk about dark matter, the problem and the solution.
Yeah, okay. And this is, I think, a very interesting topic because it is a very actual one, which makes, as far as I can see, the physical community presently very nervous, because more and more the impression is that we have a physical problem here which has no solution, and that makes it interesting. And I see the community looks very nervous to me. Dark matter, yeah, okay, it's presently the most urgent pressing problem of physics, that is my impression. The problem is old, it's well established since 90 years. But there is no theory in the air now which could possibly explain this phenomenon. That is a surprising thing. So is there some panic? Sometimes I have the impression there is panic. But we have a solution, I hope. What is the problem of dark matter? Just to repeat it again. Observation missions show gravity effects around galaxies which deviate from Newton and Einstein. It is in excess of gravitation in relation to Newtonian physics, and this excess of gravitation cannot originate in baryonic matter, which is generally assumed to cause gravity. So the main cases which we observe and which keep people busy are the rotations of galaxy clusters. They are rotating the galaxies in the cluster orbit themselves. Then the stars around galaxies, which are also moving too fast in relation to the masses which are involved. And a part of these phenomena, there are further different cases. We will present a solution here which solves all cases and is in conflict with no case, but I must say it has also its price. But I will show it this one to you. The way to start with. All cases of dark matter which we observe have a common property which is surprisingly ignored by the physicists. We will take this one to have a better understanding what dark matter is. The main original cases of dark matter are the rotation of galaxy clusters and the rotation of stars around galaxies. Here we have the cases as pictures. Left, there is the galaxy cluster. Cluster is the famous APL2261. It has almost 300 galaxies in it. They rotate and they orbit each other, and they are doing it too fast. And the other case, which is more popular in the normal discussions, is the rotation curves. Here we see a diagram. The ordinate is the speed of an orbiting star around the galaxy, and here it's the distance from the center of the galaxy. And what we normally expect is what we know from planets. If a star is orbiting, the speed of the star to keep it equivalent in equilibrium depends on the distance. So the farther the farther star is away, the lower is its speed, like we know it from planets. But what we observe is something completely different. These stars have here the measurement of the stars, are the measurement points. The rotation of the star, the rotation speeds are much higher. That is one surprise, and the other one, the rotation speed is not going down if the distance is increased. And here's a line fit through these measurement points. These are the two cases which are in discussion and must be solved. Okay, we have further indications of dark matter, and we mentioned them, and also perhaps every time to talk about them later. There is a too fast generation of stars and clusters. In the generation, in the cosmological history, at some point stars and clusters were originally below because the matter has contracted after the Big Bang. But these generations that are much too fast, too many stars in an early time, too many clusters at an early time, which cannot be explained by the existing masses which should do the contraction. So it's assumed also here that there's additional matter which causes this more speedy generation of these things. Another thing is the allocation of dwarf galaxies around is rare. Dwarf galaxies are galaxies which are around the big galaxies, and they have, one assumes that they have a circular allocation around the galaxies, but that is different, and it's not understood really why it is different. Then nucleogenesis, that also has to do with the history of cosmology, this is generation of the cosmology processes. That is the generation of nucleons, which also came too early compared to the models which we have with normal matter. Bulk cluster is a very popular case of dark matter, and also an interesting, we'll talk about this later. And then there's Renzo's rule, which has to do with illumination of galaxies. So there are two theories presently in discussion about this. The less popular is the first one, which is here, is the modifying Newton dynamics, and here the assumption is that the law of gravity changes from 1 over r squared, as we know from Newton, to 1 over r at a certain distance or a certain weakness of the galaxies, of the weakness of the gravitational field, of course. And the other more popular explanation theory is the existence of dark particles, which are particles which only interact with their gravitation, so they are not visible to us. So, problems with one, first touch the problems. The problem with one is that there is no physical reason given why this change should happen from 1 over r squared to 1 over r for the gravitational law, that is specifically okay. And the other thing is this transition point between 1 over r and r squared and 1 over r, it has to be at the order of a galaxy. So galaxies have different size. So the law must be in the way that at different sizes, at different distances, or at different field strengths, this transition happens. And for this, we cannot see any physical reason. But it's still under discussion, this theory. The other theory, the popular one, is the dark particles. That means, as I said, particles are particles which only interact with gravity, and so they are not visible. The cosmological models tell us about this contribution of both particles, and the rule is, or the result presently is, that baryonic matter, that is the matter which we know in physics, and we can treat in physics, is only 1/6 of the universe, and dark matter is the rest of 5/6 in the universe. So that means that we only know very little about our universe, which is not very satisfying. And I've omitted here the question of dark energy that makes these numbers even more curious. So these numbers are questionable anyway, and we'll perhaps have time to come back to them. The problems which we have with the dark particle theory is there's absolutely no indication of their existence, despite a very intensive search in the last 10 and 20 years. There have been a lot of experiments generated, very intensively searched for these particles, but not the faintest indication was found up to now. Then we have the bullet cluster, I will come to that later, which is not compatible with the idea of having particles. And the dark particle theory says that there is a peak distribution of them in the center of galaxies, but that is in contrast to the observation, so something is also wrong there. And also the dark matter should peak in the center of dwarf particles, dwarf galaxies, but the distribution is flat there. So the intensive search for a new particle, we'll come to this now. there's a big number, as I said, of experiments running presently searching these particles. But up to now, not the think this indication is given something. This is one, now the biggest experiment which is running at present. This is a big container which is filled with, like that thing is the name, filled with 10 tons of liquid xenon. And the idea is that in this big container, from time to time, a dark particle should anyway make some interaction, maybe elastic bump, or making a true interaction with another particle, so that in some way charged particle is accelerated, and so we get a little light indication. And here up on bottom and on top, there is a huge collection of Foti multipliers, and one expects, if happens something, that there some indication comes. This experiment with a big team of 250 specialists is now running, I think, a bit more than 1 year, and not to see this indication, no indication was given. So this search again turns out to be without success. This is now said to be, it is in fact the most sensitive of the big man. Hello? Yeah, hello? Yeah, hello? Do you have a comment? Do you have a comment? No, Mr. Are you done? No, Mr. Are you done? What? No, I have no comment. I'm talking here.
Sorry.
Can you mute him? He's got echo, he's muted.
So, is that question or not? Otherwise I will continue.
Continue.
So, there are many others, I think dozens of experiments with research, but this year is the biggest one, and now very well known, but without any success, as it was always with the search of dark matter particles. So, direction of a solution, I see a way to find a solution, and that is the distribution of the dark matter, which has a specific property, and we'll come to this. Again, here we have our rotation curve. Here we see again, this is what is expected with classical gravity, and this is what here up the element points which are detected, and the line is fitted through them. And this line here in the middle is the difference between those. It doesn't look like a difference because the addition here is a square addition 1, but it's correct here. So this is what is missing, and what is now assumed to be dark matter. It's called here the halo of dark matter. And it has this flat run is something which is very interesting, which we have to look at, because we can conclude from this flat shape what the distribution of dark matter particle is, and that is very simple. If the particles are distributed spatially by 1/r², we get exactly this line. This is fitted from this calculation. Here we have a little difference because we assume that the galaxy is has this sharp edge, but of course it is washed out, so that makes a little difference. But here it's quite perfect fit for this assumption that the distribution is 1/r². And that is something we should have in mind. Now we look at this galaxy cluster A2261, and it was investigated by the Clash Corporation very thoroughly, and they have investigated by gravitational lensing, and to produce a mapping of the dark matter. Gravitational lensing, and this is this galaxy I've shown earlier, where the galaxies are rotating, not here, okay, the axis of this rotation is not perpendicular on the screen, but flat, but that doesn't matter too much here. Okay, so this team has used sophisticated programs to determine the parameters of the light sources and the deflection, and so the density of dark matter. by gravitational lensing. I think you know it, I repeat it to you again. And we know that light is reflected in a gravitational field, and from the degree of deflection we can calculate the masses which are involved in this deflection. And what the result is normally here, that the masses which are concluded from this deflection is greater than the mass which is visible by the visible objects in this area. So this excess is of gravitational field compared to the classical field is assigned to the dark matter. From the determination, one can make a spatial distribution of dark matter, as I already said, and build maps of it. And this cooperation has done it, and the result is this, I think, very interesting picture. This picture shows the mass which was detected by this landing in, here's the mass indicated on a logarithmic scale in relation to the distance from the center of this cluster. And you see it goes up to about 3,000 kiloparsecs. Here I've indicated the radius of a galaxy is typically this here about 8 kiloparsecs. It goes a long way. It's a big cluster, and we can see how far it goes. In this area, which is indicated here, we have the cluster situated, and the cluster is built by a big mix, of course, of baryonic and matter and gas and other things, and also, of course, of dark matter, which is everywhere. But outside of this area, we do not have any normal material, no baryonic matter, no gas, nothing else. So anything which causes, and we have a gravitational field here, is caused by or is dark matter. I've forgotten to say one thing. This is just the indication of the strength of the gravitational field, but it is not indicated here as a field strength, but as an equivalent mass which is necessary to cause this field strength here, which is observed. Okay? And that is now very interesting, because we can now have a look to this dark matter distribution outside of the area where normal matter is, where the space is empty. And if we build here at the slope again is this relation 1 over r squared. And that is what we already have for the rotation price. So this is the interesting point, I think. We have now this distribution 1 over r squared, either from the middle of the galaxy or from the middle of the galaxy cluster, for the spatial distribution of matter. And this is interesting because this is measured from the center of the galaxy, as I said, in clusters. But these centers are also the center of the luminosity of these objects. So it is the distribution of photons. And what we see here is dark matter has the same spatial distribution like photons. That is, I think, a very interesting thing, and we have to see what we can conclude from it. And it means physically that, to say it again, the distribution of dark matter is the same as the distribution of photons. So, how can this happen? And my first question, can there be a pairing between dark matter particles and photons? That means every dark matter particle has a photon and every photon has a dark matter particle. No, this cannot be, because photons move at the speed of light, whereas massive dark particles cannot do so. So, what can be the conclusion? Now, we have a radical conclusion, and this is the photons themselves are the particle of dark matter. And that means, of course, we need a different theory of gravitation, in the way that gravity has to be independent of mass, and that in the way that every elementary particle contributes equally to the field. That's of course very surprising, but it has consequences which are interesting, because here we have again our rotation curve. Now, we have seen here that the distribution of dark matter here is this way, 1 over r squared, but also the distribution of photons is the same, because the center of the galaxy is also the center of the light in the galaxy. Now we can make the correct calculation with this new gravity law, which I mentioned, where we assume, it's the only assumption here, that a photon has the same gravitational field like a heavy elemental particle, like the quark equation 1, proper one. And if we do this, then we get this result here again, but with the additional result that this height of the curve is exactly where we observe it. We observe this line here, this field strength. That means we can, if we make this assumption, not only reproduce the shape of the dark matter particles, but also the absolute field strength caused by these dark matter particles if we make this assumption that photons have the same properties of gravity like a heavy particle. And this is now a quantitative result. And this, I think, is the only, to my knowledge, the only quantitative result of any theory and assumption about dark matter which exists in our present discussion. There's no other theory presently in discussion which comes close to this, to such a thing that we have a quantitative result. So we have further problems with some particles. I will quickly go through them. That is, this is a bulk cluster. I think you know it. It's shown many times in talks. Here have been two galaxies which have passed each other, and here we have it was observed where the baryonic matter is and where the dark matter is. The dark matter is here colored in blue, and one can see the dark matter moves in front of the baryonic matter. And the question is, how can this be? One could say it's not possible that these heavy particles are faster than the normal particles which build gas particles which build the galaxy. The other argument which says, okay, it's a good indication, say, okay, this gas which builds the galaxies was decelerated by friction, but the heavy particles here are not decelerated by friction, so it's plausible that the dark particles are in front. But one has done it more thoroughly. There have been simulations calculated for this case. This is a possible process, and the result of all these simulations was no, it is not possible. If we assume make this assumption, this heavy particles, the normal particles of galaxies, it would never turn out to be this way. On the other hand, when we assume that dark matter particles are photons, of course they are in front, because photons are always faster than electrons. That would be what we also explain the Albrecht law. Okay. Another problem is dwarf galaxies around the mother galaxies are distributed around should be distributed according to the theories around the sphere, around the mother galaxy, and in fact they are a layer, and that is also not in conflict with the present theories, but that is also a more complex and difficult problem. So, and then we have Ranzo's rule, which is also very interesting, I think, because it has to do with luminosity. It says in the original form, for any feature in the luminosity profile there is a corresponding feature in the repeating curve and vice versa. To say it in simpler words, it means that in parts of a galaxy with less luminosity, the rotation speed is reduced, and so is the gravitational field. And this is a direct indication, I think, of a photonic gravity. Summary to this point, the present model of dark matter particles explains some cases but is in conflict with others. The theory 1 explains only a few cases but is in conflict with others. The conclusion is none of these can be correct. The photon model explains all the current cases and is with no case in conflict, provides quantitative results in contrast to all other theories, and it requires, of course, in order to its gravitation, which of course is however question astronomy with gravitation. So, my personal history, how did I come to this? I did not find the theory of gravitation to solve the dark matter problem, but it was the other way around. My action was to extend the Lorentzian relativity towards gravitation, which is normally not done, and the result was a Lorentzian gravitation which does not depend on mass. And then I was aware of dark matter, and I was surprised myself that this Lorentzian gravitation also explains the dark matter problem. Next step is now, what is the time? Gravitation without mass. I would like to explain something how this works with the gravitation without mass, because that is unfamiliar to any one of us who has learned and studied physics. First, the other question, why is gravity related to mass? That was once done by Newton, and it was obvious for Newton that gravity is related to matter. But matter needs a measure. That measure could not be the volume of the matter. So Newton did not have an alternative to mass when he wanted to characterize matter, to quantize matter. Elementary particles were unknown to him at this time. The new theory was very surprising. Originally started by Einstein in 1911, because in 1911 Einstein started to find a new way towards gravitation, and he did it by looking to the reduction of speed of light in a gravitational field. Yeah. And when he continued on this way, he made a mistake because he deduced an equation for the reduction of speed of light in a gravitational field from energy conservation. And that was wrong. This reduction is also the direction dependent. Einstein could not know this, he had not recognized this and was taken it into account. And so Einstein could not continue what he noticed obviously. So Einstein returned to the Newtonian understanding that mass causes gravity, and he produced his theory of gravity based on the curved spacetime. But with this correct equation, which Einstein had wrong, all aspects of gravitation can be deduced, including the relativistic ones, and so also the results of gravitation. That is surprising that the work of the law was not taught any further, which is in conflict with this result. So gravitation as independent of mass is a proper solution. So how does this work with this very big speed of light? We know the Shapiro experiment, there one can measure the reduction of the speed of light in the gravitational field of the sun in this case, and this is the equation. I think we know them also as a result of, was finally the result of Einstein, but I think it's understandable. Yeah, should I explain now? I think you understand this equation. Here it has a power of 1.5 depending on the direction, and that was what Einstein didn't know and has led him into an error, but we can do it now with the correct one. I have also to explain that I use a particle model because we have an oscillation in elementary particles, and this oscillation is very essential for the understanding of gravity. And this particle model is built in the way I have explained in other cases. An elementary particle according to this model is built by two massless subparticles which orbit each other at the speed of light. And we need some further conditions and constraints which we have to fulfill, and we end here by this particle model, which I use. One of the results is, for instance, is this motion is speed of light, and in the motion given by the Lorentz effect, Lorentz transformation, because it's a heating flow of the circuit, very simple. And another thing is, this is a good model to deduce the inertial mass of the particle, because the inertial mass of the diffusion, every object which has extension has necessarily inertia. That is not a possible idea or theory, but it is inevitable that an extended object has inertial mass, that it has to do with the binding forces which must be in every extended model. And from this model I can also calculate the mass, inertial mass of the particle, and that is a very successful calculation, because from the electron, for instance, it yields the mass of the electron with a deviation from the measurement which is less than 10 to the minus 50. And this equation is a very simple one. The mass is only depending on the size of a particle, and it has as constants Planck's constant in the speed of light and nothing else. It's such a simple equation, it is so successful compared with Higgs, where you have nothing like this. Higgs does not give us any numerical results. Okay, now again to gravity. Here we can, with our relation, induction speed of light, we can think that we have spheres around the sun, and these on every surface of a sphere, the speed of light is constant. Now, if we let go light-like particle like a photon through this area, what will happen? Very classically, it happens reflection, and the reflection is easily calculated from this equation to derive it in some proper way, and we get for the acceleration which falls from this reflection this value. And you see this is a Newton's value for gravity. And Newton has postulated this relation. We have here deduced this relation. I think this is something new. And if we integrate this path from here to here for this angle of deflection, we get this famous deflection 1.75 seconds, which made Einstein once famous because he has predicted this. And everyone then believed him in this space-time curve, space-time assumptions, but this is classically gives us the same result. So this is a particle in motion, or we look at the particle like that. Okay. Here we have our particle now without the subparticles in the air at some place. Now we switch on the gravitational field, and now this motion is reflected down, and this is a progressive spiral down, and this the acceleration down is we can think it is the particle which has passed the sun and now it is wound up. We have some imagination what's going on here. Okay, and the acceleration here again is this value of Newton, which we have also deduced here, rather than postulating. And we can see here that this acceleration does not depend on the mass of the particle. The mass of the particle is reflected by the diameter of the particle, and irrespective of the diameter of this particle, the acceleration is always the same. So this is a weak equivalence principle, which by the way we have also taken. Okay, now the question, what is now gravity? Gravity, and that I think is now quite clear, is the change of the speed of light in a gravitational field. That is the cause of anything which has to do with gravity. So, why is the speed of light reduced? Okay, Einstein has postulated it, we will again try to deduce it. Here we have a particle, light-like particle, can be a photon or another different light speed particle. And now we have two elementary particles here. And now the following happens. These here are the forces which bind these subparticles to each other. And these are this is a multiple field, fields are attracting and repelling forces in a random sequence, and they react also with these particles, so this particle is a random zigzag walk, and of course in this walk, the speed of the light is the average speed. And we can calculate this because this is a statistical process, and we know the statistical rules of such a process. And if we do this, we end up with this equation. This is the consequence of this statistical consideration. This is almost identical to the equation of Einstein from Newton. With the difference, here is the mass, and here the number of elementary particles, and of course a different the deduction here of speed of light is independent of the radius of the causing elementary particle, because the forces here, that's part of the model, are always the same, only the configuration is a bit different. And so this indicates, or this is a reason that this gravitational effect is independent of the mass of the causing particle, which is the source of the gravitation. Okay? This is in contrast to Einstein, this equation, who followed the principle of energy relativity, not such thing. Okay, now we'll tell you only one thing about this new way of general relativity, and I use here the Schwarzschild solution. I think you know the Schwarzschild solution is a reduction of Einstein's field equations to a spherical symmetric object like the sun, because that can do a lot of things and it's much simpler than the original equations of Einstein. And these are normally used to make the following calculations. The perihelion advance, the gravitational lensing, black holes, and other things. Yeah. And this is an interesting thing, and we will show how we can deduce this equation from this Schwarzschild solution, from the assumption of Lorentzian relativity. This is the Lorentz equation, the time-related Lorentz relation, say for a single particle. Okay? We convert it a little bit because we need polar coordinates. But that's nothing, but that's all what we do here. Now we switch on the gravitational field to the Now we have the reduction of the speed of light, as it was explained, in the different direction, and also reduction of the extension of fields. Fields contract by this fact that the speed of light is differently reduced in different directions. And these changes are now applied to these single elements. And we get this here. These four fields, show it here. It's not difficult, we can do it very easily. And now we reorder it a little bit, and we get here the Schwarzschild solution as I have shown it on the previous slide. Okay? Okay, this is the deduction of the Schwarzschild solution in this way. We normally do it in the way of Einstein, and I show you that is this way here. This is, I have copied this, all the equations which are used for this deduction from a textbook, from a popular textbook, and these are more than 80 equations. And the complicated thing is here we need the Riemannian geometry for four-dimensional space-time, and here Einstein's field equations. That's very complicated. I do not know many physicists who are able to do this, but there are some who can do it, and if they do it, they end up here also with the Schwarzschild solution. Or alternatively, we do it this way. And why do it? Why should we do it? Why should we do it with Einstein if we can do it with this way? It's much simpler, we can do it in school, with Einstein, not in school, I think. But the best thing is not that this is simpler, the best thing here is that this is a deduction from known physical laws and facts, We do not need new principles as Einstein has used them to come to this result. Okay. So, now a summary of anything. Now our main topic was dark matter. I summarize the results for dark matter once again. The present model of dark matter particles explains some cases but is in conflict with others. The bond theory explains only few cases. I forgot to say also the rotation curve can be explained by bond, but you need a different one for every gravity, for every galaxy in that case. That is a bit unsatisfying. And so it is in conflict with other cases. The conclusion is none of these both theories can be correct. The photon model, I call it photon model, explains all occurring cases of which we assign to dark matter and is with no case in conflict. It provides quantitative results in contrast to any other theory, but it requires, of course, an ordered theory of clarification, which, of course, on the other hand, solves other questions which I did not touch. So, that was it, and I thank you for your attention. And open for questions.
Thank you, Albrecht. Can we put the... Yeah, can we just get everybody on there? Thank you.
Well, I think you can... how do we do this?
Does he have to stop?
Well, I think maybe he has to stop sharing.
Yeah, can you stop screen sharing now, Albrecht?
Yeah, I can stop it, but perhaps I'll question to my slides.
Yeah, well, he can always come back to share.
Yeah, okay. Do we have any questions from the audience here or from the virtual audience? Or comments?
I think it was a bit too much in one time.
Well, we don't know. We got a question from Roger.
Okay.
Huh?
Yeah, Alexander Uxinger has gone back to looking at Einstein's 1911 work and is going with a variable light speed theory. Is it related to what Alexander Uxinger is saying?
Sorry, I could not hear you very well.
Okay.
Is your work related to Alexander Utzinger's work using variable light speed theory?
No, unfortunately not, because I did not know that. But I should look into it, yes, to see if there are parallel thoughts.
Okay. He's written a book called Einstein's Lost Key.
Yeah, that is from Alexander Unziker.
Yeah.
He has written this book.
Yeah.
I found this book later on and found it very interesting, but my consideration would have been earlier.
Okay. Thank you.
Okay. Anybody else? Anyone from the gallery, the Rogues Gallery? Yeah. Any of the usual suspects?
If there's none, perhaps I can add something which I've announced but now forgotten during my talk. That was this phenomenon of Zitterbewegung. When I have shown my particle model where two subparticles are orbiting each other, this motion in an electron, for instance, is called by Schrödinger Zitterbewegung. And this word Zitterbewegung is in German not a good word because it has no good relation to physics. Schrödinger has used it because he felt in a very uncomfortable situation. That is what I have concluded from his paper. Schrödinger has learned, as I think most others also, that an electron is a point-like object. And on the other hand, and he thought by mechanics, that the electron has an oscillation. And there is a conflict between this oscillation and the fact that it is a point object, because point object normally cannot oscillate. And he didn't feel comfortable, he didn't know how to handle it, and so he has used this very unclear German word Zitterbewegung. Okay, he could set an oscillation also, but that would be too clear. What is zitter in Germany is a motion which I make if I'm very cool, okay. This is very irregular, and this was by intention, I think, of Schrödinger to use a very unsharp word, so that he is not, has not settled anything about physics by using this word. That is my understanding of it.
Okay. Any further comments, or in which case I will say thank you, Albrecht, for an interesting presentation.
Okay, thank you.
If you're ready, Lou, you can start immediately.